So we're talking about properties of logarithms. The first theorem that we deal with says log of any base of 1 equals 0. So log 1 equals 0. We can prove that to you. Write it in its other form. X to the 0 power equals 1. We know that anything to the 0 power equals 1 except 0 itself. Single logs, when we talk about single logarithms, they have one argument with a coefficient of 1. That's our definition for what we talk about as a single logarithm. Sometimes we need to use these properties to write things as a single logarithm, and if we don't, or if we don't know how, based on the definition, we won't be able to answer the questions. Get it in the right form that we need it in so that we can solve. Well, expanded logarithms, there's another definition. Expanding a logarithm is to do the opposite of writing it as a single log, and an expanded logarithm involves splitting the arguments up. So an expanded log has the arguments split up based on the theorems that we talk about, and only allowing 1 for the exponent of the argument. So when you get done, you will only have an exponent of 1 on all the arguments. I'll show you what I mean by this single log and expanded log thing in here in a second. Here's a theorem which kind of shows you an example. On the left here we have what's called a single log. And on the right we have an expanded log. This theorem says that if you take the log of a product meaning multiplication, you can split that up into two separate logs that are being added together. Now, this can be used in either of two ways. We can use this to split it apart and expand it, or we can take the expanded form and then put it together and get the single log form in case that's more useful to us. Let me get you an example. Evaluate log base 6 of 2 plus log base 6 of 18. Now, I have no idea what the exponent is on 6, which gets me 2. Absolutely none. I mean, 6 to the first is 6, so it's got to be a decimal. So that's probably pretty doggone ugly. Log base 6 of 18, well, 6 to the second is 36. So that's somewhere between 1 and 2. So we got something between 1 and 2 and something smaller than 1, between 0 and 1. That's pretty ugly. But if we were to rewrite it as a single logarithm, because I see addition, I can use that property and I can multiply the arguments, the 2 and the 18 together, giving me log base 6 of 36. Now we know that equals a number, and we can rewrite that if we don't know. 6 to the x equals 36, which is 6 squared. Therefore, the sum of those two logarithms is 2. Now, I have no idea what the individual parts are. I have no idea what that is. I have no idea what that is. But when I add them together, boop, I end up with 2. Let's see here. Theorem. The next theorem talks about division. When you're dividing the argument, you can separate that into subtraction. An example of that would be evaluate, sorry for all the scribbling, log base 6 of 72 minus log base 6 of 2. Well, if I write it as a single log, 72 over 2, then I can get to something that I know how to solve. Whoa, looks super duper familiar. So I don't know what this part is, and I don't know what that part is, but their difference is 2. Okay, the next theorem They made a song about this one from the movie Madagascar. I don't know if you remember this one, talking about moving the coefficients to exponents. You are allowed to take the coefficient and make it an exponent, or take the exponent and make a coefficient. I think you remember the song. I like to move it, move it. I like to move it, move it. Yeah, it's about logarithms and exponents and coefficients, so you keep that in mind when you're watching that movie next time, you know. So, yeah, that's where you see real life and logarithms coming into play, and I know that is going to impact your life in a big way. All right, example 2. Rewrite p without logarithms. So, rewrite p, no logs. So, what I want to do is get a single logarithm over there on that side. So, let's see here. We got 1/2 and, oops, sorry. Back up. I'm going to do something with this 1/2. I'm going to use that property, the one I just talked about. I'm going to move it up and make it an exponent. So this is the natural log of t to the 1/2 minus the natural log of 6. Of course, we're dealing with base e because it's a natural log. And because I see subtraction, then I can divide t to the 1/2 over 6. Remember, I'm only dividing the arguments. Don't ever think that you take a log divided by a log. Now, I know that we see something like that in the change of base theorem, but that is not the same property as what we're dealing with right now. So remember what we started with, the natural log of p. I hope that you understand that p is equal to t to the 1/2 over 6. That is rewriting p without any logarithms. The last thing that we need to talk about is something called linearizing an exponential function. We will talk about why we're going to do this, but let me just show you what to do. We can take any base logarithm of both sides. We typically only do base e or base 10. We're going to do base 10 in this example. And so we're taking the logarithm of both sides. Well, I can see that there's a product right there, a times b to the x. So the first thing I'm going to do is break it up using my log properties, log a plus log b to the x. Well, this is an exponent. In order to be in expanded form, we need to move that down in front. So that would give me log a plus x log b. Now, I don't know if you're familiar with y equals mx plus b, which is the equation of the slope-intercept form of a line. If I would rearrange this, keep in mind, log a is a number. Log b is a number. Yes, I know, that means you have to know what a and b are. So what we have is log b times x plus log a. So we have changed this into something that looks very linear. This is called linearizing. So, example 4 is the opposite of that. It's going backwards. It's starting off with something that's in the linear form, right? You got log y and then mx plus b on this side. And they want it to be rewritten into an exponential function. So we're going backwards from the process we just talked about a few seconds ago. So in this case, to get something out of its log form, what are we going to do? We're going to rewrite it into its exponential form. 10 to the 3.1, plus 0.03x equals y. Just for fun, I'll put the y on the other side. Well, if you remember your algebra, when you add exponents, that means that you must have been multiplying like bases. Multiplying like bases means I can add the exponents, so that must have been what it looked like. And we can even go one step further, because we've got multiplication in our exponent right here. We can write this as the power, oops, sorry for the scribble, power of a power. So we were supposed to write it a times b to the x. So what's a? 10 to the 3.1. So what do you got there? 1258.925. And what do we have for b? 10 to the 0.03, 1.072. Round things to the thousandths place, and that'll make things better. Thank you.